so today we're going to be talking about topic models, a very specific example of how we can cluster discrete data where each observation can have more than one cluster. And so the motivating example for topic models is, suppose that you have a huge number of documents. Say that you have emails from a corrupt corporation or from a corrupt politician. You don't know what's going on in that set of emails. You want to figure out what are the main themes being discussed in that set of emails. And you can't read them all. And another example of how you might use topic models is to figure out all of the New York Times articles from the 90s. How do you figure out what are the main themes being discussed there? And so topic models allow you to get a corpus-level view of the major themes, to cluster them into themes, even though these themes may co-occur in several of these documents. And like everything else we've been talking about for the last week, this is unsupervised. You don't know what the topics are a priori. We're not doing classification. And so what we'll talk about today is what are topic models, how do you know if you have a good topic model, and then how to go from raw data to topics using Gibbs sampling. Okay, so let's say that your input data looks something like this. You have a bunch of documents where each document is a collection of words. And you also have an input integer k, the number of topics you want to discover. And so the output that you get is, for every topic, you get a bunch of words associated with that topic. And so this is a lot like the means of k-means that we were talking about last week. This is one topic, and here are the words that are most probable in that topic. And then the other output that you get is, for every document, what are the topics expressed by that document. So here we have technology topic, business topic, and an arts topic. The business topic over here, the technology topic over here, red light, green light, a two-tone LED to simplify screens. This document is all about the technology topic. As you move to the right, you get things that are more businessy. The three big portals begin to distinguish among themselves as shopping malls, is a mixture of technology and business. And then as you move to the center, you get all three. Forget the bootleg, just download the movie legally, talking about technology, business, and the arts. And if you were looking at a huge document collection, you figure out what topic you're most interested in, and then you start looking at the documents that are relevant to that topic that you're interested in. And you can do this on other data sets. Here are topics from the journal Science. So one about genetics, evolutionary biology, and then computer models. And topic models have been used in industry to look at e-discovery in court cases, for companies trying to monitor what people are saying about them online. You can also use it in academia. It's been used for figuring out the meaning of words, segmenting discourses into what people are talking about at time A versus time B, when do politicians try to change the subject, things like that. And also machine translation. So sometimes in different domains you'll have different translations of words. Topic models can tell you whether you should translate mouse as a thing that squeaks, or mouse as a computer accessory. And as we'll see at the end of today, inference is relatively simple. And you can do it in about a week, as you'll do in your homework assignment. All right, so you can also think, so any questions thus far?
Are topic models useful for things, for data that aren't words? Is it used in like other situations where you might need multiple labels on a
yeah, so for a long time, topic models were also used for image processing, and you could think about the objects in an image as words, and so you could get like beachy words and city-y words, and that for a long time was a state-of-the-art approach for processing images. Topic models have also been used for biological data, and in fact, they were invented for biological data. And J.M. Pritchard came up with the underlying model that we'll talk about shortly, and you can think about the kinds of things that appear in a genome as words, and you can have different collections of those things in different organisms, and you can use this to understand what genes co-occur together.
Cool.
Another way of thinking about topic models is as a matrix factorization. You have a huge collection of documents. That's an M by V matrix with a bunch of, with M documents and V words. And you're trying to find a low-dimensional representation of that, where you have these relatively thin matrices of topics and words. So the topics are assigned to documents. Each document has a distribution over topics. And then each topic is a distribution over words. And you're trying to find the topics that allow you to best reconstruct your overall data set. And if you use SVD to do this, this is called latent semantic analysis, very popular in information retrieval, and some of the folks who came up with that, Thomas Landauer in particular, were here at Colorado in the psychology department, which is cool. Okay, so, but that's not what we're talking about today. We're going to talk about a different way of doing this using a generative model. And so, like naive Bayes, we're going to tell a story of how our data came to be in a sequence of probabilistic steps, and we'll use posterior inference to uncover the latent variables z, as you mentioned last week, that best explain our data. And so this was developed in a paper called Latent Dirichlet Allocation, and so what they did there was they took latent semantic analysis, LSA, popularized by folks at Colorado, and just replaced the S with a D to create LDA. And so that's how this approach got named. Okay, so, but where is this D Dirichlet coming from? So we talked about the Dirichlet process before. That's a generalization of a Dirichlet distribution, which we'll talk about in a little bit more detail here. And so the Dirichlet process is a very general thing. Usually when we talk about the Dirichlet distribution, it is a distribution over multinomial distributions. So the Dirichlet process is this very general distribution over distributions. Who cares what the underlying distribution is? The Dirichlet distribution by itself is usually just a distribution over multinomial distribution. So a little easier to get your head around. So here are some multinomial distributions. We can think about multinomial distributions as living in this triangular space. And so if you have distributions that favor one outcome over all of the others, it lives in one of these corners. Okay? And then we can also have uniform distributions that live in the center, and we can have any distribution. So if we have a distribution that is uniform over two of these dimensions, but zero probability for the other, that's living on the edge. And so what the Dirichlet distribution does is give us a distribution over all of the places where a multinomial distribution can land. And these multinomial distributions come from a Dirichlet distribution. So this is the math. Let's not go through the math. Let's look at pictures. We'll parameterize the Dirichlet distribution by a vector. For a moment, let's talk about the Dirichlet distribution as having a scale and a center. And so if the scale multiplied by the center gives you a vector of all ones, this corresponds to a uniform distribution. And we can go back to the math and see why that is. So this is our distribution. And if all of these are ones here, then we're basically raising this to the 0th power. And that results in everything being treated equally. You don't care what this p is. Everything is equally likely, and so you get this uniform distribution. All multinomial distributions are equally likely. And if you crank up your scale, then you get more and more centering around whatever your center is. But what is more interesting is when this alpha gets smaller and when the center moves around. And so if you move around your center, you can get distributions that are focused on particular kinds of multinomial distributions you want. But what's really interesting is if all of your alphas are less than 1, you get a preference for multinomial distributions that are far away from the center. So what are these distributions? What does it mean to be far away from the center in this picture?
It would mean you would prefer one or more of the corners and strongly disprefer at least one of the corners.
Yeah, exactly. And so that's absolutely right.
You only have one label, like if it's just business or technology or arts.
Yeah, or you might have 2 labels.
Or 2, 1 or 2.
Yeah, and so this is nice because this sort of corresponds to our intuitions about how people write documents. It's not that you'll have a vector with everything with a non-zero entry. When you write a document, it's going to be about 1, 2, maybe 3 things, but it's not going to be about all 200 things with small little proportions. And this is how it's different from latent semantic analysis, this matrix approach for doing this. This basically made no assumptions about it, and you basically had an entry for every topic in a document. And so this is why latent Dirichlet allocation can work better than latent semantic analysis. And it's also easier to implement, which is another nice bonus. So here's another picture of sparsity where we actually have a dot for every multinomial that we're drawing out.
And this alpha is similar to the alphas we've been working with in last week's lecture, where they kind of concentrated about one distribution or another.
Exactly, yes.
Okay.
Yeah, and so they're exactly analogous. Yeah, so if you have smaller alpha, you will be more selective in the things that you draw from your base distribution. And the math works out nicely, and so if you condition on data and you have a predictive distribution over what will come out of a multinomial that's drawn from a Dirichlet, you can work through the math and get it so that you have your prior, your alpha, being added to by the things that you observe. So as you see stuff, it's basically reinforcing your prior. And so once you see data, it's basically just adding to your prior, and this will make inference quite a bit easier. Okay, so our generative story for how our data came to be is we first have some topics. We draw our topics from a Dirichlet distribution with some prior. Then, for every document, we draw a distribution over topics for that document from a Dirichlet distribution. And so this is saying, where does it land in this space? And mostly we'll have documents that are about 1 or 2 things. And then, once we have a distribution over topics for a document, for every word in our document, we'll choose one of these topics to generate that word. So Hollywood might come from the arts topic, download from technology, buy from the business topic, and so on. And then when we generate this word, we're looking at a topic, and then this topic is a distribution over words, so we select a word given a multinomial distribution given whatever topic we're using. And so this is this story in a slightly more formal form. Each topic has a multinomial distribution over words. Each document is a multinomial distribution over topics. Each word is drawn from a multinomial distribution for that document. And then each word is drawn from the multinomial distribution specified by the topic. And so you look up what topic you're supposed to use for this word. That selects which topic you're going to use, and then that tells you the word you're going to use. And this way of drawing a probabilistic model is called plate notation. So we have plates that say how many times each of these things are happening. So we have K topics, M documents, and N words in each document. And you'll notice that the only thing that we observe are the words, and our task is to try to figure out what these Z's are and what these betas are. And also what these thetas are. Okay, so just to recap what we've talked about so far, topic models, two components, association of words to topics and documents to topics. And we need to figure out how to use statistical inference to figure out how to fill in the missing pieces of this story. So questions thus far?
No.
Okay, all right. So, one question you might have is, how do you know if you have a topic model that's good or not? One thing you can do is you can have some held out data. So this is like the test set that we were doing for classification. And each of these models can generate this document. And you basically ask, hey, model A, model B, model C, generate these documents, and that will give you a probability. So, and the higher the probability, or the log probability in this case, the better it was at sort of anticipating what data will come next. Another thing you can do is you can actually show these to human beings and ask them to, say, look at a topic. Then you'll stick what's called an intruder word in that topic, and then you ask them, can you find the word that doesn't belong? So this is like the Sesame Street, one of these things is not like the other, one of these things just doesn't belong. And ideally, if the topics made sense to begin with, they'll be able to find the word that didn't belong. And so you can do this on Mechanical Turk. You can ask people to do this online. And now you can get a sense of what makes a good topic. So this is a good topic. And this is a bad topic. So here, no matter what word you put in here, people always clicked on taxis instead. And so taxis just doesn't fit with the rest of this topic. And so one really interesting thing is that this measure of topic model quality doesn't correlate with the predictive task. And there's actually a negative correlation, which is really interesting. And so basically the moral of the story is that if you want to use topic models for prediction, use a prediction task. If you want to use topic models for showing people what's going on in a corpus or for yourself, then you should use techniques like model precision and not the held out likelihood. And so, or if you're, whatever task you care about, measure that. And so, so this is typically not something that's talked about in an intro machine learning course, but this is sort of my research area, so I just wanted to mention that, and if anyone wants to talk about that more, I can talk about this ad nauseum. But anyway, let's move on, if there are no questions, to the task of inference. Okay, all right, so the task of inference. So we need to figure out what these Z's are, given our data and parameters. Okay, so in this case, our latent variables are the topic assignments, the topics themselves, and each document's distribution over topics. And so we can break this down into a joint. And now what we want to do is we want to figure out what each of the latent variables are. And so we'll use Gibbs sampling again. And just like last time, we'll condition each topic assignment on the topic assignment of all of the others. And we'll use the same convention of removing a particular latent variable by doing this minus sign here. So everybody still okay with the notation?
And when you do negative D in, is that removing two of them, or?
Well, so no, it's just removing one, but that's a good question. It becomes a little more complicated because each document has a bunch of words. So this is just removing, say, the fourth document from the fifth, sorry, the fourth word from the fifth document.
Okay.
So there's only one word, but to know what that word is...
You need two indices.
Exactly,
okay.
Yeah. Okay, so, and now here's sort of the picture version like we did for the Dirichlet process mixture model. So we're going to take a word, pretend we don't know what the topic is, unassign it, as it were, then compute the conditional distribution depending on all of the other words, then choose a new topic for that, and then repeat, repeat, repeat. Big picture okay? All right. So, when we work out the math, it looks something like this. So, the conditional distribution is you have the probability of both things happening. So, the new thing being assigned, or this word being assigned to a particular topic, and the assignments of all the other topics in your documents. And then you divide by everything else. So that's the definition of conditional probability. There's a lot of math here that isn't well served by these slides, so we won't go through excruciating detail, but the goal is to give you a big picture and to hopefully make sure that it isn't completely implausible. So what we'll do is we don't want to sample the distribution over documents topics, and we don't want to sample the topics distribution over words. So what we do instead is we'll integrate these out just like we integrated out the means in the Dirichlet process mixture model. And so this integral looks messy, but it isn't that bad. There's a problem with the slides. Arg. So this is actually a gamma function on these guys. And this gamma function is a generalization of the factorial.
Continuous factorial.
Exactly, yeah. And so the nice thing about this is that you basically have everywhere there is a little bar here, these should be gamma functions. And there are a lot of them. But the basic form is that you have gamma functions that are only off by 1. And so you have gamma functions where some things are +1 over things that are not +1. And we can use this identity that, so here the gamma, this is the only place that the gamma is actually showing up. So you can reduce gamma of z + 1 over gamma of z to be z. And when we do this, we have these +1s in some cases and not in other cases. And so things cancel in such a way so that you end up with a conditional probability that looks like this.
Are all these gammas showing up because of the combinations that we're doing?
The reason that they're showing up is because the normalizer of the Dirichlet had this gamma in front. And so when you integrate the multinomial with the prior plus the counts of the number of times a particular topic uses a word, if you integrate that out, you'll get something that looks like the normalizer of the Dirichlet, which has these gamma functions. And so this is just so that it's actually a distribution in sums to 1. That's where the gamma function is coming from.
And why does the normalization factor? The normalization factor has the gamma.
Mm-hmm.
Why is that? Is there any kind of like tie back to how we're leaving one out and picking all the others, or anything like that?
No. So the fact that we're leaving one out is where these plus ones are coming from.
Okay.
So that's where the plus ones are coming from. The reason that the normalizer for the Dirichlet has a gamma is because you're basically counting up the number of ways that you can have a distribution that satisfies the constraints of summing to 1. And the discrete analog of that is you have a factorial. And in the Dirichlet, you have continuous multinomials, but you can still only have so many of them being greater than 1, or sorry, greater than 0. And so you have the same analog there, and you're using the factorial or the gamma function to count up how many non-zero components you can have in your Dirichlet and still make it sum to 1.
Makes sense.
Okay. So let's go through this equation that rendered poorly on the previous slides. I'll fix that before I post it. So the end result is that there are two main terms. And so this term is how much a document likes a topic. And this is how much a topic likes a word. And so here we have the number of times document D uses a particular topic. Here we have the number of times a topic uses a particular word type. Then we have the priors, so this is saying how many topics a document on average likes to use. Then we have a prior for the topic, so how many words a topic likes to use. And then altogether, how much this document likes topic K, how much this topic likes the particular word. So let's go through a toy example of Gibbs sampling for LDA. So let's say we have a document, and we start off assigning topics randomly. And then we do that for all of our documents. Now we create counts from all of our documents, and this corresponds to this term. How much does each topic use each word? So topic 1 uses Etruscan once, topic 2 uses Etruscan 0 times, and topic 3 uses Etruscan 35 times. And now for a document, we're going to sample this word, so the word trade. It currently has topic 2. So first we unassign it, and so we'll reduce the count of the number of times topic 2, because it was using topic 2, uses the word trade. So that goes from 8 to 7. And now we don't know the topic of this word. And so now we compute the conditional distribution. First we look how much does the document like each topic. And so it likes topic 3 a lot. It uses it twice. It likes topic 1 a lot. It uses it twice. And so we have that encoded in these bars here. Why isn't topic 2 0? It isn't used in this document at all.
Wasn't that the original value of trade? Or
right, so that is gone. So it used to be 2, but that is gone. It doesn't exist because we're conditioning on probability of ZI equals to 2 given all of the assignments that aren't that word, and there are no topic 2s anymore. So this is non-zero. Where is that coming from?
I don't remember where, but I imagine that must be coming from a uniform prior over all topics.
Yeah, so not exactly uniform, or well, it could be
a prior.
Yeah, a prior. Yeah, and so this lambda. Oh, sorry, no, this alpha here is saying you're adding in a little bit of mass to every topic, even if it doesn't get used. So if this is 0, it's not used in this document at all. It still has a little bit of weight. And so now we look at how much each topic likes the word trade. So topic 1, topic 2, and topic 3, how much does it like this word? So this is corresponding to this part of it. And again, there's a prior term in there. So this is corresponding to the Laplace smoothing that we talked about. So this could be 1. If it were, that would be Laplace smoothing. And then this would be the size of vocabulary. And then we multiply those things together. And we can represent that as a rectangle. And so topic 2 likes the word but is hardly used in this document. Topic 3 is used a lot in this document but doesn't really like this word. And topic 1 likes it on both counts. So we sample with probability proportional to this purple area, and we choose topic 1. So now we're going to up the count of trade in topic 1 and increase the count in this document. So the blue bar gets wider because it's now used in this topic. This topic is used in this document, and the red bar gets longer because this word is used in this topic. And sampling from a distribution, not that hard. So you basically compute a real number for each of the topics. You normalize it so it sums to 1, and then choose a random number between 0 and 1, which you can easily do in Python. And then you choose the topic that is less than this number but extends to a point beyond that number, once you've normalized these and summed them all together cumulatively. So any questions? Okay. So here's the algorithm that we just walked through. You have a bunch of iterations. For each document and each word, you decrement the old counts, you sample a new assignment, and then you increment the new counts.
What would be the terminating condition for this algorithm? When do you break from this loop?
When you get tired.
Okay.
So just like Gibbs sampling for Dirichlet process mixture models, you basically run it until things stop changing too much, but you never know when you're really done.
Okay. So you store some kind of comparator between the previous state and your current state. And
yeah, or another thing you can do is you can compute the likelihood, and it will look something like this. So it won't monotonically increase, and so it may go down, goes up, goes down, up, but eventually it will start leveling off. And when it does, you might be done. It's always possible that you could go along for a long time and then whoop, you go to someplace better.
It could suddenly have a breakthrough that one
Exactly.
word actually is like CDs is not business, it's technology.
Exactly. Yeah, and it figures that out, and then other dominoes fall into place, and then everything changes.
This sounds like it could have huge applications to stock markets because just suddenly just like these big jumps and breakaways and
yeah, and so a lot of statistical analysis has been applied to the stock market, and Martingale theory came out of looking at time series in financial data. So yeah, those folks love probabilistic models. There are some details that we're not talking about. So how do you choose the alphas and the lambdas is pretty important, and you should actually probably sample them too. How you initialize is also important. You should probably do it randomly. We already talked about how long do you keep sampling, and so you can look at the likelihood, but that isn't always perfect. And then how many times should you run this algorithm? So you can start over from scratch. How many times should you do that? You should probably do it more than once.
Did you say something on lag and burn-in?
Oh, yeah. So do you take your final answer, or do you take, or do you average over all of the things that you've seen in your sampling process? So that's the question here. So, and there's a lot of opinion on this. I will link to an optional reading that has my opinion on this, but there are many different opinions on this, and people disagree vehemently.
But probabilistically, is this the same, running this algorithm for 1,000 iterations, is that the same as running, averaging 100 trials for 10 iterations, or like did you want to?
So in theory, once you have reached convergence, all samples are equal. In practice, they're not, and so you can have different strategies to sort of maximize the bang for your buck, or bang per your computer cycle. And so, in my opinion, you should have many chains, and you should take many samples from each of those chains. But there is huge disagreement on this, and some people will say just have one chain, have a very large lag, and just sample from that every 10,000 iterations or something. This is a matter of opinion, so I will link to my opinion, but everyone should be aware that there are many different opinions on this. There are lots of good implementations out there. So mallet is in Java, LDA C is in C, and I have some code that I need to get off Google Code now in Python and C++. So lots of implementations out there. I would not use, however, GenSim, which is in Python. That is not the best implementation out there at the moment. Okay, and in class, we'll talk more about topic models as a way to uncover themes in large document collections. We'll walk through an example of Gibbs sampling on your own. And next time, we'll talk about different inference techniques that you can use to approach these models, in particular variational inference, which is an alternative to Gibbs sampling.